Now we have 5 elements in our circuit. We have 3 resistors and 2 capacitors. But we only have 3 constraints. We have omega naught, H naught, and Q naught. To satisfy these 3 constraints with 5 elements, we have an infinite number of possible selections. If we want just a single solution, what we could do is pick 2 of the components and solve for the remaining 3. Now the equation for Q naught was pretty complicated. In fact, all the equations are pretty complicated, but the ratio of omega naught to Q naught was just equal to this expression, which is a lot simpler. And so maybe this is a good place to start. Capacitors don't have as many values to select from as resistors, so why don't I pick these 2 capacitors to be equal to each other, to be a standard value that I have in my parts box. Then I could solve for R5, be equal to, put that on this side of the equation. That would then bring this over here as Q naught over omega naught, and then I would have, here I'd have 2 of these, and then just let C4 equal C3, so I'd have 2 over C3. What I have is picking the resistor R5, depends on the filter specs of omega naught and Q naught, divided by my first pick. Now if it turns out that the first pick was resulting in R5 being impractical, we can go back and pick a new value for C3 and try it again. The next most complicated equation was for H naught, and H naught was equal to 1 over R1 over R5 times the quantity 1 plus C4 over C3. So I'm going to put the H naught here and the R1 over here. Picked C3 to be C4, so that's just equal to 1. I've got an equation for R5, it's actually equal to this, so it's 2Q naught divided by omega naught C3. The 2 and the 2 cancel here. Bring the Q naught in the numerator, and I've got Q naught divided by H naught omega naught C3. If R1 turns out to be impractical, I could pick a new value of C3. Given my 3 filter specifications, I'll learn how to pick these shortly, and my initial pick, I can then pick R1. I want to keep my resistors roughly between 1K and 1 megohm. If things are smaller than 1K, we tend to draw too much current. If they're above 1 meg, tend to have noise in our resistors, and that begins to degrade our audio signal. Now we have one more component left, that's R2, and take a look at solving for it. Take a look at the equation for omega naught squared. We have an R2 in there, so we could use that equation to solve for our last resistor R2. Multiply this over here, and then bring the R1 on the other side of the equation, minus 1 over R1, and we got the value of 1 over R2. Again, let's substitute in the value for our components that we've already solved for, and just try to get this selection in terms of our previous pick of C3. I've got omega naught squared, I've got C3 times C3, so C3 squared. R5 was equal to 2Q0 over omega naught C3 from the last page, and R1 was equal to Q naught divided by H naught omega naught C3. I have some terms canceling here, so I've got an omega naught squared and omega naught, so that cancels, gives me omega naught, 2Q naught, and then C3 squared and C3 just gives me a C3. And then I just got this term over here. I can pull out a common omega naught C3, left with a 2Q naught, H naught divided by Q naught. R2 is going to be the reciprocal of this expression. R2 then is 1 over this. Multiply numerator and denominator by Q naught. I get a Q naught here, omega naught C3, 2Q naught squared, and then the Q naught canceling. You can see that this resistor could possibly go negative. I've got another constraint to worry about, and that's the values of H naught and Q naught. But this is implying that for a positive resistor, that 2Q naught squared is greater than H naught. Or we could solve for this is that Q naught needs to be greater than H naught over 2 square root. So given the 3 filters design parameters, we can come up with a design procedure. But we have to just check that Q naught is greater than the square root of H naught over 2. But if it isn't, we have to go back and do a different design procedure. In other words, we wouldn't pick C3 to equal C4. And there's an infinite number of procedures. You just simply have one here that's fairly simple and using 2 capacitors that are equal to each other. We'll do that. We'll pick standard value that's in our parts box, and then our values of R5, R1, and R2 are a consequence then of our equations, and our values of H naught, Q naught, and omega naught, and our initial pick of C3. And just reiterating what we had above here is that if you do get an impractical result, just pick a different C3. If this isn't true, then you have to actually do a different design procedure. Maybe you got to pick C3 to be twice C4. You have to play with that to find the right combination. In Chapter 13 of ECE 202, we learned that any periodic waveform can be written as an infinite sum of sine waves through a thing called the Fourier series. What I'm going to do in this lab is to take a square wave, actually pull a sine wave out of it. Turns out it's quite easy to generate a square wave in electronics, and we'll see an example of this in ECE 303 lab. But I grabbed the expression for the Fourier series for this particular wave shape, and it's the following. It's equal to 4v maximum over pi, where this is the v maximum value. The summation from n equals 1 to infinity of 1 over n times the sine of 2 pi n f times t. Here n is equal to an odd number, in other words 1, 3, 5, 7, and so on. Suppose they have a 2 volt square wave at 100 hertz. Well, Well, then evaluating this equation for n equals 1, I'm going to have 4 times 2, which is 8, divided by pi, 1 over 1, and the sine of 2 pi 1 times 100 times t. The next term is when n is equal to 3, so we get 4v maximum. 4 times 2 is 8, divided by pi, and then divided by 3, and then the sine of 2 pi 3 times 100 times t. And so on with a 5 and 500 and 7 and 700 and so on. What you can see in this expression is here I've got this sine wave at 100 hertz, but the one at 300 hertz is a third as big, a fifth as big, a seventh as big. As we take our other harmonic terms, they're smaller in value and keep getting smaller. So although technically we need to have an infinite number of sine waves to produce a square wave, but in reality we don't need an infinite number, but just a lot of them. So in our design, what we'd like to do is to recover a sine wave from a square wave, this particular 2-volt square wave. And to do this, we need to eliminate the 300, 500, 700, 900 hertz sinusoidal components that are in our square wave. Now, a filter can't really eliminate a particular signal, but it can make it a lot smaller. So let's use the idea of attenuation to get rid of these terms that we just have the fundamental frequency at 100 hertz. So back to our equation on page 1 for the magnitude of the transfer function for the bandpass filter was equal to this. Now we're operating at a frequency that's greater than omega naught, and our value of Q naught is generally a number greater than 1. If that's the case, what I've got here is an omega naught minus omega squareds, but we're saying that omega is bigger than this. Difference will be dominated by this term, and we're going to square it and square, so you get the fourth power. Now, this term here just has an omega squared in it, with an omega naught over Q naught, but omega naught is smaller than omega, so this term here would be smaller than having just omega to the fourth power, because I've got an omega squared and omega naught squared. You can roughly approximate this denominator as just this term right here, minus omega squared, squared square root. The squaring and the square root, get rid of the minus sign, just have an omega squared, and then I've got an h naught, omega naught, divided by q naught. I have an omega, and then I have an omega squared. That's going to cancel, it's left with an omega. So this is roughly the value of my gain at a frequency greater than omega naught. If omega were equal to 3 omega naught, it's going to put in a 3 omega naught here. The omega naughts cancel, and I get h naught divided by 3 times q naught. So this is the value of my gain for the frequency of 300 hertz. And so my gain at 300 hertz is h naught over 3 q naught. And I want this 300 hertz signal to be attenuated. So let me make this number big enough relative to the value we had at the center frequency, which is just equal to h naught. If I make this denominator 30, in other words, make q naught equal to 10, then the gain at this frequency is 1/30th of what it was at the center frequency, and my third harmonic is smaller than the fundamental, so I will get some attenuation. Now, is this enough? Well, we'll have to see whether it works or not if we can get a pretty clean sine wave out of our square wave. This is how I'm going to pick the value of q naught. Now, suppose that I want from this 2-volt square wave a 10-volt sine wave. So my scale factor with the fundamental frequency was 8 over pi, which is 2.546. So for a 2-volt square wave, I'm going to get out a 2.546 peak sine wave. I need to multiply this by some number to get 10. That's my gain of h naught at the center frequency. That means that h naught is about 4. I've got f naught, which is the frequency of my square wave. I've got q naught of 10 and an h naught of 4. So these are my parameters for my filter. Let's check that this inequality is satisfied. So I've got a q naught of 10, h naught was equal to 4, so this is equal to 1.414, and of course 10 is greater than that, so our procedure will work. We don't have any negative resistors. Pick C3 equal to C4. I'll pick a 0.047 microfarad capacitor in our parts box. I'll solve for R5, which is 2 times Q naught, which is 10. Omega naught is 2 pi times 100, and C3 is 47 nanofarads. And that's 677.255 K. R1 is going to be equal to 10 divided by H naught, which is 4, 2 pi times 100, and 47 nanofarads, and that's 84.657 K. And lastly, R2 is 10 divided by 2 times 10 squared minus 4 times 2 pi 100 times 47 nanofarads. That's 1.728 K. Now these are not standard resistor values, and the nearest standard resistor values are 680 K, 82 K, and 1.8 K. Next, I'd like to show you a technique for measuring phase using what's called a Lissajous pattern method. Now in our circuit we have input and output voltages that have different amplitudes and different phase angles, but one thing they have in common is the same frequency. If that's the case, it's possible to actually measure phase relationships and actually frequencies by plotting one voltage versus another. Suppose I have a sine wave times an amplitude of C and a frequency of omega, and I'll call that X, and that y is a different amplitude and a different phase angle. Now if I were to plot y versus x, I get different types of shapes that look like ellipses. And if you take the ratio of this value to this value as the arc sine, you can get the angle if it's between 0 and 90 degrees for this value of theta. Likewise here, if you had b and a, 180 minus the arc sine of a over b gives you the phase angle if it's between 90 and 180. Now on the oscilloscope, we actually can disable the time base and put a voltage there. Now the theory for all this is quite complicated, and I'll leave that as an outside exercise if you're interested. What we're going to do is just take a look at a very special case, shown right here. If the phase angle is 180, you end up getting this ellipse just becoming a straight line. What's interesting, if you had a phase angle of 90 degrees and b and c were equal, you get a circle. And if you had a phase angle of 0, that straight line would be passing through the origin, but in the first and third quadrant. What we're going to do is tune our circuit, and as we pass through our center frequency, we'll see the relationship passing through a straight line. Let's try to prove this. I thought I'd just run some spice simulation to show you that it works with just some known values of sine waves and phase shifts. Let me zoom on this so you can see it a little bit better. So here's my spice file. What I'm doing is I'm creating a sine wave with a phase shift of 45 degrees. What I'm generating is a sine wave with a difference of 45 degrees in angle, and also two different amplitudes, an amplitude of 1 and 2, and you can see the relationships down here. But when I plot one versus another, I get this in ellipse, and I get my intercept here is about 2, and my intercept here is 1.414. So if we take the arc sine of that ratio of a to b, you end up getting 45 degrees. This next picture to the right is the same file, I just changed the angle to be 90 degrees. If these two amplitudes were identical, I'd get a perfect circle. So you get some interesting shapes on the screen by plotting one sine wave versus another of the same frequency. On the bottom left, I change the phase angle to 180, as you can see down here, and I get a line that passes through the origin between the second and fourth quadrant. We're going to use this particular shape to find the tuning of our circuit to see where the actual center frequency is. So it's possible to actually measure phase angle with this technique, although we're going to use a different idea in lab, and I'll introduce this in ECE 303. What's interesting also is if you take two different frequency sine waves and plot one versus the other, you get a variety of different shapes. And depending on the relationship between the two frequencies, you get different types of configurations. And you could actually figure out a table of different types of pictures that would tell you relationships between frequencies between two sine waves. Now we have a computing capability in our oscilloscope, and so we can actually calculate and measure frequency quite easily. But this is a technique that was used before the instruments we have today. Again, this is a very old technique, but sometimes when you're doing a research problem, having ideas from the past can sometimes give you some insight into solving current problems. So it's always interesting to learn ideas that were used extensively in the past, but not particularly now for what we're doing in the same application. But things can change in the future, and just having that wealth of experience can help you design all kinds of things. We'll go back to our full screen again. So the purpose of lab number 7 was to take a look at active filters, which are used extensively in audio preamplifier circuits and test instruments. They consist of resistors and capacitors and op-amps, and they can realize things that we could realize with a resistor, capacitor, and an inductor. But also in addition, we can also have gain, which we can't do that with a passive circuit. Now the concepts we covered was the multiple loop feedback filter. We developed a design procedure for picking components, and we looked at using a Fourier series to model a periodic waveform. The techniques we're going to learn in lab is using the XY feature of our analog discovery scope to display a Lissajous pattern for tuning. We're also going to use the network analyzer option in the analog discovery to do a Bode plot. Now at the end of this lab, there's another exercise, just to call your attention to this. This is a P-Spice assignment. What I want you to do is to take the values of your components that you've measured and simulate your circuit and measure the value of F0, H0, and Q0 and compare that to what you measured in lab. There's a very similar example in supplemental problem 12.5 in the ECE 202 ebook. This is lab number 7, a bandpass active filter.